Scalar product can be defined as the product between two vectors, and the results will be a scalar quantity. There are two definitions for scalar product: geometric definition and algebraic definition. For geometric definition, if we have here two vectors, vector A and vector B, so each vector have its length and its direction, which is specified by the end arrow of each vector. So we can write down geometric definition of the scalar product as A dot B. So this is why sometimes we called the scalar product as dot product, because it has the dot process. This would be equal to the magnitude of A times magnitude of B multiplied by the cosine of the angle between the two vectors, which is here the angle theta. So this is the geometric definition of the scalar product. On the other hand, for the algebraic definition, if we have a vector A can be represented by its component ax in the direction of a bar x plus ay a bar y plus az a bar z, and for the vector B can be written as bx a bar x plus by a bar y plus bz a bar z. So in this case, the dotted product A dot B would be just the multiplication of the components in the same direction. So we can write as ax bx plus ay by plus az bz. This is the algebraic definition of the dot product or scalar product. If we take an example, if A equal to 3a bar x plus 4a bar y and vector B equal to 2a bar x plus 3a bar y plus 6a bar z, A dot B would be 3 times 2 plus 4 times 3 plus 0 times 6, because the z component of vector A is equal to 0, and this would be equal to 18. There are different applications of dot product. One of them is to check if two vectors are perpendicular or not. So if we have here vector A and vector B, and the angle between them is 90 degrees, by recalling the law of the dot product, which is A dot B, length of A times length of B cosine the angle between them, which is here 90 degrees. So in this case, the result will be 0. So if the dot product between two vectors is equal to 0, in this case, the two vectors are perpendicular. Another application is to find the angle between two vectors. So again, A dot B is length of A times length of B cosine theta. From it, we can find the value of the angle theta as cosine inverse A dot B over length of A times length of B. Another application is to find the work as we know that the work is equal to the force times the distance. This law can be applied only if the force is in the same direction of the distance. But if we're having a force that have a certain angle with the distance vector of moving the object, so in this case we need to analyze the force into two components. The first component is the perpendicular component, and the other component is the parallel component. Now, if we want to find the value of the work, then it will be equal to F parallel as magnitude multiplied by the distance also as a magnitude. We choose the F parallel because the force needs to be in the same direction of the distance vector. The F parallel can be represented by the vector F multiplied by cosine theta. This is the F parallel, and it's clear from this figure here. By rearranging the above equation, we can write down W would be equal to F multiplied by d cosine theta, and this is similar to the scalar product law, so we can write W as F dot d. The work is just the dot product between the force and the distance vectors.